This video is going to provide a summary of the how does a compass work topic. So in this topic you've learned all about compasses. You've seen that compasses are really just small magnets. So we started by learning a little bit about magnetism. You know that like poles repel, so two north poles will repel each other, and unlike poles attract, so a north and a south pole attract each other. We saw that magnets can only be found as dipoles, so there's always a north and a south pole joined together. We've seen that magnetic field lines are a very useful way to represent the magnetic field. The more magnetic field lines we draw, then the stronger the magnetic field. You've also learned a little bit about ferromagnetic materials. So not all materials are magnetic. Not all metals even are magnetic, but metals like iron and cobalt are magnetic as they're ferromagnetic, so they can actually hold a magnetic field. After this, we had a look at the Earth's magnetic field, as compasses work by detecting the Earth's magnetic field. We've seen that the Earth's magnetic field is actually very important for our survival here on Earth. It helps protect us and the rest of the planet from cosmic rays, which would otherwise cause a lot of damage to our bodies. What actually causes the Earth's magnetic field is an active area of research at the moment. It's broadly understood to come from currents in the outer core of the Earth, but the exact mechanism is, as of yet, not really understood in all its details. After that, we started to have a look at electromagnetism. This is because this electromagnetism is going to link this topic to the next topic that you'll be looking at on nuclear power plants. So you need to understand this to understand how power plants work. So we had a brief look at a bit of the history of electromagnetism. You saw that initially it was thought that there was two separate forces, an electric force and a magnetic force, and then Maxwell realized that these could be combined into one theory of electromagnetism. So currently physicists would really like to combine all of the four fundamental forces, the electromagnetic, strong nuclear force, weak nuclear force, and gravity, into one combined theory, which is sometimes called a grand unified theory. But this is also an active area of research. There's no really convincing way to do this as of yet. It's very hard to combine gravity with the other forces. So after a brief introduction to electromagnetism, we looked at some of the formulas that are involved. We saw that we could calculate the force felt by a charged particle in a magnetic field using F is equal to BQV sine theta, and then using the right hand rule to get the direction of that force. For a current carrying wire in a magnetic field, we saw that the formula used to calculate the size of the force is F is equal to BIL sine theta, and again we can use the right hand rule to get the direction, though in this case your thumb represents the direction of the conventional current, whereas for a charged particle this represented the direction of the velocity of the particle. We also saw how to calculate the magnetic field around a current carrying wire. We saw that magnetic fields circulate around a current carrying wire, and the strength is given by mu naught I over 2 pi r. To work out the direction in which it circulates, we can use the right hand screw rule. And then because a current carrying wire is generating a magnetic field, if we put another current carrying wire near it, this second current carrying wire is going to feel a force, and the size of that force is given by F is equal to mu naught over 2 pi times I1, I2, L on D. And we saw that this force was attractive if the currents are flowing in the same direction, and repulsive if the currents flow in opposite direction. Finally, we had to look at how we could build solenoids, just long coils of wire, and that solenoids are very similar to bar magnets. The magnetic fields look almost identical, except the great thing about solenoids is that the magnetic field can be turned off and on. So these can work as electromagnets, which can be switched on and off very quickly. And so we can now get magnetic fields turning on and turning off, which is used a lot in everyday life around us, such as at car dump yards. So I hope you've enjoyed this topic. The next topic you're going to be looking at is how a nuclear power plant works, and we will be building on some of these ideas about electromagnetism in that topic.
Thanks to Sebastian Frick for filming this video.